In this video, I'm going to run through SC26, which is the final chemistry topic, and it comes up on paper 2. It has been highlighted as one of the topics that will definitely be on your exam, but luckily it's short and it's very straightforward, so it shouldn't pose any huge difficulties. This is a specification. The start of it is about nanoparticles, their size, their properties and the risks, and then at the end you need to be able to use data to compare the properties of ceramics and glass and metals. So we'll start with nanoparticles, and we'll start by looking at the size of nanoparticles. So you do need to know that to be considered a nanoparticle, the particle has to have a diameter between 1 and 100 nanometers. And as well as knowing that range in nanometers, you also need to know it in meters. So 1 nanometer will be 1 by 10 to the minus 9 meters. And then 100 nanometers will be 1 by 10 to the minus 7 meters. And if you want to do that on your calculator, if you're not good at working in standard form, it's just 1 by 10 to the minus 9, which we said was 1 nanometer. And then if I times that by 100, I get 1 by 10 to the minus 7 for 800 nanometers. So that's the actual range, but just in terms of how that compares to other things that we come across in chemistry, an atom would be much smaller. An atom wouldn't be in that range, so an atom would be smaller. So too would a molecule. A molecule made up of a couple of atoms would be smaller. And then you have got a nanoparticle. So an atom would obviously just, for example, if we looked at hydrogen, that would be one atom by itself. A molecule, something like NH3, so it's obviously bigger because I've got 4 atoms. And then when you're talking about a nanoparticle, you're usually talking about a few hundred atoms in a nanoparticle. So it would be smaller than something like a giant ionic lattice. In a giant ionic lattice, something like NaCl, you would have billions of ions. So a nanoparticle would be smaller than that. And remember, it's the diameter that we're talking about, 1 to 100 nanometers diameter. Just to compare the nanoparticle to a few things you might come across in biology. So a nanoparticle would be smaller than, say, a bacteria. It would also be smaller than a human cell. Roughly the same size, so DNA would have a diameter within this range, so would a virus, so would protein. So some of the things that you will find inside a cell would be around the same size as a nanoparticle. They would be within this range. Something smaller, just that this came up in the 2021 paper, they asked about a starch molecule. Again, because it's a molecule, implies that there's less atoms in it, and a starch molecule will be smaller than the nanoparticle, which we said would be a couple of hundred atoms. So that's a nanoparticle in terms of size. So I have written this out on the first page of your booklet. The only thing you would really need to highlight here would be the scale, 1 to 100 nanometers in diameter, and that is typically just a couple of hundred atoms. We've got an example because we did learn about carbon nanotubes back in CC7. They would have a diameter between 1 and 100 nanometers, so they would be considered nanoparticles. The other thing we need to look at is properties of nanoparticles, and the important bit here is that they have a high surface area to volume ratio. So we're going to look at this little graphic here on the left so I can explain what I mean by that. We've actually seen something similar to this before when we looked at CC14 and we looked at rates of reactions, and we saw that if you had, say, a lump of metal, if you got that, let's just say I have 5 grams of my metal, if I got that metal and I broke it up into smaller pieces, so I still have the same mass of the metal, but now I've just got it in smaller pieces. We said that this was increasing the surface area, and when we increase the surface area of a solid, we also increase the rate of the reaction. And the reason for that was when you cut it up into small little pieces like this, you have got an increased surface area. There's more atoms exposed to the reactants. In the big lump, only the atoms on the very outside of the metal are capable of reacting. when you cut it into small pieces, a lot more of those atoms that were originally on the inside now get exposed and are able to react. So by increasing the surface area, more particles come in contact with whatever it is that they're reacting with, and that increases the rate of the reaction. And we've got something similar here. You can see here on the left, I've got 3 cubes, which are all the same size. So they've got the same volume, meaning they take up the same amount of space. And I've got the volume here, 64 for each. And if we look at the first cube, it says that the edge length is 4. So I'm just going to assume that that's 4 meters, or I'm going to call it meters. The edge length is 4 meters. So what I can do is I can take that edge length and I can work out the area of the face. So to work out the area, it'll be 4 times 4, and I get 16 meters squared is the area of one face. And this cube has 6 faces, so 4 around the edge, 1 on the top, 1 at the bottom. So I have got 6 times 16, giving me an answer of 64. So I can say that the entire surface area, 6 times 16 is not 64, 6 times 16 is 96. So I can say that the entire surface area for this cube is 96 meters squared. And then if I take the next cube, directly next to it, you can see it's the same size, the total volume is the same, but the surface area for this one is a lot bigger, and that's because they've cut them up into smaller pieces. So instead of having just one cube, we've now got 1, 2, 3, 4, 5, 6, 7, 8 smaller cubes. So it says here that the edge length is only 2, so the edge length will be there, and that'll be 2 times 2 gives me the area of the face will be 4 meters squared. But each cube has got 6 faces, as we saw, so that's 4 times 6. That gives me 24 meters squared per cube. And I've got 8 individual cubes. That makes it 24 times 8 equals 192. So by cutting that up into smaller pieces, I am massively increasing the total surface area. And I do the same again here. Again, volume is exactly the same, but I've cut them up into lots of individual cubes, and that massively increases my surface area. And then the final calculation you can do is surface area to volume ratio. So you take the surface area and you divide by the total volume. So that would be 96 divided by 64, 192 divided by 64, 384 divided by 64. And that allows you to compare the surface to volume ratio of the 3 cubes. And we can see here that this one at the bottom has the highest surface to volume ratio. So what difference does that make? Does it make much of a difference? The answer is yes, for the following reason. When you've got a greater surface to volume ratio, you've got a greater proportion of the atoms available to interact with the substances they come in contact with. So it was similar to the example I talked about before. In the original cube, most of the atoms are in the center. They don't come in contact with anything, therefore they don't react. Here you cut them into small little pieces, and a lot of the atoms that were inside in the original example are now exposed and are able to react, and that's massively going to speed things up. So nanoparticles do have this as property, high surface area to volume ratio, but as well as knowing that property, you need to be able to link the property to the functions of nanoparticles. So one thing that nanoparticles can be used for is a catalyst. So again, we've come across catalysts in CC14. They lower the activation energy and they increase the rate of the reaction. We don't need to know how catalysts do that, but one thing that they can do is they can absorb reactants onto their surface, and by doing that they bring reactants in contact with each other, and you get more frequent collisions and more frequent successful collisions. That's just one way that a catalyst works. So here we've got that because the reactions take place on the surface, you don't need to know anything more about it. You just need to know that reactions take place on the surface of a catalyst. So if they're taking place on the surface, the bigger that surface, the more collisions there are going to be, the more frequent successful collisions you're going to have. So that came up in November 21 as well. They were asked why nanoparticles could be used for catalysts. You'll say large surface area, more space for collisions on the surface of catalysts, therefore it'll increase the rate of reaction. Something else nanoparticles can be used for, and this does get asked quite a bit, sun creams. So sun cream blocks the UV rays from the skin, which prevents sunburn, also prevents skin cancer. if you're answering this question, you have to mention that it blocks UV rays. If you just say it blocks the sun from your skin, you're not going to get the mark. You have to specify the type of ray. And then the other advantage is the fact that nanoparticles are so small, you can't see them on your skin. So if you could, you'd end up obviously like a kind of a white paste on your skin because it's so small. Once you rub them in, they're invisible. So you don't even know, you can't see that you've got the sun cream on. Nanomedicine, so I did mention this earlier. Nanoparticles, these particles are smaller than cells and they can be used to get into cells, so they can cross the cell membrane, and for that reason they can be used to deliver drugs to various different cells. Computer chips, small and conduct electricity, so actually whether they conduct electricity or not will depend on the atoms you've got making up your nanoparticles. We saw with carbon nanotubes that they have delocalized electrons, so could conduct electricity, but that won't be true for all nanoparticles. They can also be used as plastic and sports equipment, makes them stronger without adding much mass. Again, these nanoparticles are small, they're light, you can strengthen without adding mass, so keep your sports equipment nice and light. So far they've asked about catalysts, they've asked about sunscreen, they haven't asked about the other three, so I would just know all of these 3 bullet points and know the uses of nanoparticles and how it links to their properties. Other thing you need to know about nanoparticles is the effect that they have on the health. They are a new technology, haven't been around that long, so we don't know much about their long-term effects on health. Just because we haven't been using them long enough to know that maybe slowly but surely they are going to damage your health, but they don't have any short-term effects and long-term effects aren't known yet. The other thing is, again, because they're so small, they might be able to pass into your bloodstream, getting through the skin and across cell membranes. There's so many chemical reactions happening in your body. There is a fear that the nanoparticles, if they enter your body, that they can change the chemical reactions. As I mentioned, they can act as catalysts. So if they got inside your body and they start catalyzing different chemical reactions, they could kind of mess up that balance. So there is that fear also with nanoparticles. So this whole page is basically about nanoparticles, and that takes up half of the specification. So not a lot of content there to learn. The bits that I've highlighted are key. But if we scroll down now, these are all of the exam questions I can find on nanoparticles. So we'll just run through a few of them together. Particles less than 100 nanometers in size are classified as nanoparticles. So we've already seen that if the particle is between 1 and 100 nanometers in diameter, it is a nanoparticle. So then they want you to do a conversion from nanometers into meters. So we said that 1 nanometer was 1 by 10 to the minus 9 meters. If we have got 100 nanometers, I'm going to have to times that by 100, and I'm going to get 1 by 10 to the minus 7. And again, you can do that on your calculator if you're not good at working with standard form to be able to work that out. Nanoparticles can be used in some sun creams. Describe a reason why they are used in sun creams. I mean, the most important thing you want your sun cream to do is to protect your skin from UV rays. So that's what you're going to be mentioning. Don't say protect from the sun, you have to specify UV rays. So protect from UV rays because UV rays can cause sunburn and can cause skin cancer. The other thing you can say is that the nanoparticles are really small, so when you put them on your skin, you cannot see them. So if we just flick to the mark scheme, I'll just show you exactly what it says when I find it. Where is it? Oh yeah, here we go. Can absorb or block UV light from your skin. So it reflects UV light either, but don't just say sunlight. Therefore that prevents against sunburn, or it prevents skin or cell damage, protects the skin, can help prevent skin cancer. The other thing you can say again, particles are very small, therefore they appear invisible, so they can't be seen, so it doesn't look white on your skin. So that's all of the things that were acceptable there. The next question, some of them are concerned that there's a risk when you're using sun creams containing nanoparticles, and why. And as I said before, nanoparticles are new, and because they're new, we don't know their long-term effects. So that's one thing you can say. The other thing you could say is that they're so small that they can get through the skin into the bloodstream, and they could affect the chemical reactions taking place in your body. So here's the mark scheme. Do not know the risks fully, or the long-term risks are not known. Why? Because they are new, okay, a new technology, or they have not been used for a long enough time. Other risk, they might pass into the body, get through the cell membranes, enter the skin, get into the bloodstream. What's the problem with that? They could change the reactions in your body. So make sure whatever you're saying, you're then backing up. So We don't know the risks. Why? Because they're new. They might pass into your body. What difference does that make? They could change the chemical reactions taking place. It says here, ignore harm the skin, body, cause rashes, illnesses. They're not linked to doing that. They are obviously tested on the skin, and they're not linked to causing rashes or illness. The dangers that they pass inside, and they're doing kind of things that we're not aware of. Next question, again, relates to the size. So it says an atom has a radius of about 0.1 nanometers, okay, so quite a lot smaller. A nanoparticle might have a radius of about, so again, we remember that the range for the diameter is 1 to 100 nanometers. They're asking you for the radius. This one here is outside the range. 0.1 will be outside the range. 50 nanometers will be smack bang in the middle of your range. So your answer there is going to be 50 nanometers. 1 centimeter would be too long. A useful property of nanoparticles in sun creams is that they have a low surface area to volume ratio. So that's the opposite. They don't have a low surface area to volume ratio. They have a high surface area to volume ratio. So that's not correct. Toxic, they're not toxic. White, it doesn't matter. It doesn't matter that they are white. They could be green as long as they're protecting your skin from the UV rays. That's all that matters. The colour of them isn't relevant here. So the useful property is the fact that they prevent the harmful UV radiation from reaching your skin. The next one, they want you to calculate the surface area to volume ratio. So you need to take the volume, which is 51,200, divide by the surface area, 38,400, and just do that calculation on the calculator. So you get 51,200 divided by 38,400, and you get 1 is to 1.3. Now on the mark scheme, what they accept this, 1 is to 1.3 is fine. It's actually 1.3 recurring, so you can include the dot. You could write 1 is to 1.33. The other thing they accept is getting rid of the decimal. So because 0.33 is a third, if I want to make that a whole number, there are 3 thirds in a whole. So if I multiply this by 3, I'm going to get an answer of 4, which is a whole number. But if I multiply that by 3, I need to multiply the other side by 3, and I get 3 is to 4. So you can write the ratio as 1 is to 1.3 or 3 is to 4. Either were acceptable. But in order to find it in the first place, you're taking the bigger number, the volume, and you're dividing it by the smaller number, this surface area. And just make sure you're writing your answer as a ratio. 1 is to 1.3. You're asked for a ratio. Oh, what does it do? The next bit I'm going to go back over in a second. Question 4. Nanoparticles are very small. Some of them have a radius of 17 nanometers. The radius of a magnesium atom is only 0.16 nanometers. So approximately how many times larger? So you can see that 0.16, if I times that by 100, I would get 16 nanometers. So it is approximately 100 times bigger. And I mean, again, if you don't want to do that in your head, you can do 17 divided by 0.16, and you will get an answer there of 106. The closest there is 100, so D. Remember, you're only being asked for an approximation, so it doesn't have to work out exactly. A catalyst contains cube-shaped nanoparticles. Figure 3 shows a diagram. The length of each side is 9 nanometers. Calculate the surface area of the cube. So we don't specifically do this in chemistry, but it is basic math that you're expected to be able to do. You're told that the length of the side is 9 nanometers, which means going across is 9 nanometers, obviously going up and down is 9 nanometers. So the first thing you need to do is get the area of one side. So it's going to be 9 times 9. You get an area of 81 nanometers squared. There are 6 faces in total, so then you're going to have 81 times 6 equals 486. So your final answer is 486. So again, that's just kind of basic maths, getting the area of a face and then counting how many faces you've got to work out your surface area. Nanoparticles have many uses. Some scientists are concerned. One possible risk of using nanoparticles, okay, it's what we've seen before. They're new, so you don't know the long-term effects. They could pass into your bloodstream. They could, then damage cells, change the chemical reactions, all the rest of it. Just try and keep it as specific as possible. Another one relating to size. So you're asked to compare a chloride ion, a fluorine atom, and a nanoparticle. Remember, nanoparticles are typically a couple of hundred of atoms, so the nanoparticle is going to be bigger than an individual atom or an ion. So straight away I'm drawn here to D, that has the nanoparticle at the end. A fluorine atom would be smaller than a chloride ion. Fluorine atom is in period 2, so it's got 2 shells. Chloride ion is in period 3 with 3 shells. So your answer is going to be D. And the rest of these are on the other part. So that's essentially it for nanoparticles, right? You can see they ask quite a few questions about the size, a little bit there about surface area to volume ratio. Sun cream has come up a little bit, and then also the possible risks. So not a lot of content to learn, and the questions tend to be quite repetitive. So yeah, it should be a topic that you can target. The rest of this topic, again, types of materials. And before you kind of look at all this information and think, God, do I have to learn all of that off by heart? The answer would be no, okay? So if you look here at the specification, it says compare using data. So you're going to be given data. And we look at the exam questions, you'll see that. You'll be given data about the physical properties of glass and clay and ceramics and polymers and all this kind of stuff. And then using that data, you'll need to be able to answer some questions. But you don't need to learn all this information off by heart. And then, yeah, you're going to link the use and the property. Something's used because it's got properties that make it suitable. So if we have a look here, some of the materials you're going to be looking at: glass, clay, metals. So what they've done is they've gone through appearance, melting points, malleable, ability to conduct electricity, ability to conduct heat. So you'd be given something like this, a table, and then it would probably say, of these 3 materials, pick the one that would be most useful in electrical wires. All right, so if you've got an electrical wire, it needs to be able to conduct electricity. So glass can't, clay can't, so you pick a metal. You put a metal inside an electrical wire because it can conduct electricity, and that's important for a wire. I know for a window, like which one of these would you choose? For a window, you want it to allow light in, you want to be able to see out, so you're going to pick the one that's transparent. So you'll be given the data, and you just need to link the property to the use. So I've written a little bit about each one. I've just taken this from the textbook and from a revision guide. You can have a read through it, just so you become a little bit more familiar with the materials. But I wouldn't learn any of this off by heart. Metals, obviously, we did learn about in another part of the course. So they could ask you a few questions on metals without giving you the same amount of data. But it's all stuff that we've already studied. Composite materials, then, it's kind of similar to what we looked at with alloys. It's when you're kind of taking 2 materials and adding them together to make it better, to make it stronger. So for an example, reinforced concrete, you've got your concrete and you add some steel, it's going to make it a bit stronger. Chipboard, you've got your wood chips, and you hold them together using resin glue. So you're taking 2 things, kind of putting it together to make it better. And again, underneath here, talk a little bit about the different composite materials, and then talk about their uses. So this is the kind of common example. You're given a table, it gives you some properties, and then you need to link it. So I've got a worked example. All 3 materials could be used to make the frame for a train carriage. Evaluate these materials for this use. So in these types of questions, as long as you're saying something reasonable and you're backing it up, you'll still be able to score marks even if you write something different from the person next to you. So you're trying to make a frame for a train carriage. So first of all, they're looking at timber, and I said, right, well, timber's got a really low density, which makes it nice and light, so it'd be the lightest frame, which would be good. However, if you look at the strength, it's only got a tensile strength of 1, so it's much weaker than the other 2. Therefore, if you were going to use timber, you probably need quite a lot of it to get the strength. So even though it's really light, if you need a lot of it, then you could end up with a kind of a heavier frame than if you use something stronger to begin with. Then underneath here, they talk about steel, and they say it's almost as strong as aluminium. There's not a huge difference in their strengths, but you say it's quite a bit heavier. So it's going to be much heavier. If you've got a really heavy carriage, maybe the train, it won't be able to go as fast if you've got really heavy carriages. And then you've got the aluminium, which is the one that they're saying is best. It is denser than timber, but that could be, if it's denser than timber, but it's less dense than mild steel, and it's the strongest. So you won't need as much of it as you would need of timber, because it's so much stronger. and it's a lot less dense than the mild steel, and it's stronger. So you could say aluminium frame is actually most lightweight. It's also got good resistance to moisture. So it's gonna last longer. So it doesn't need to be protected. So overall, that would be the best choice. So as long as you're kind of backing up your answer with points from the data you're given, you should be fine. So if we have a look at some of the questions that have come up on this, you'll see what I mean. So this first one here, they give you this information. Which material is most suitable to use in electrical circuits? All right, so if I want to use something in electrical circuits, it has got to be able to conduct electricity, which means your choice is going to be a metal. And the answer is literally metal, and you get 1 mark for picking out metal, and then for giving your reason. It can conduct electricity, and electrical circuits need to be able to conduct electricity. And that's, if I find the mark scheme, literally all that is in the answer. Yeah. Metal, good conductor of electricity. You didn't even need to say why. Another example of a question here, all right? They're giving you lots of information, but then you need to use it. So why is this wire made of metal? So again, they're talking about a wire. It's made of metal. What's the main reason? The metal conducts electricity. What do you want your wire to do? Conduct electricity. That's what a metal can do. What type of material will be most suitable for the insulation? So the insulation, you don't want it to conduct electricity. You want to be able to pick up that wire without getting a shock. So it's important that it's insulated. So you're going to look back up here at one that doesn't conduct electricity, and you'll see you've got 3 that don't conduct electricity. So how are you going to narrow this down a little bit more? What else do you need in your wire? None of them react with water, which is good. Hardness, medium, low, and then flexibility. The flexibility one is really important. You do need your wires to be flexible. Glass and ceramics have very low flexibilities, but a polymer has a high flexibility, and it's not as hard. So I would say a polymer, because it doesn't conduct electricity and it's also flexible. So I would pick the polymer, which I'm assuming is the correct answer. Yeah, the polymer. And yeah, the reasons why the others weren't acceptable is because they weren't flexible enough. And then last question I think I've got here on this. Explain using information for figure 10. So again, you're still given all of this information in that question. Why the ceramic is suitable material to make a cup that will contain a hot drink of tea or coffee. So they're saying ceramic is suitable for making mugs. Why? Melting point is high. Right, if you're going to put something really hot inside it, you want it to have a high melting point. You don't want your mug to melt as soon as you pour tea inside it. Conducting electricity, this is irrelevant in this question, so I'm not going to comment on it. Reaction with water, no reaction. That's obviously a positive. Tea and coffee both contain water. If your mug reacted with the water and you had a chemical reaction as soon as you poured it in, that's obviously not a good thing. Hardness, yeah, it's like, it's hard, it will hold its shape, and flexibility will be low. So the fact that it's low flexibility and medium hardness is going to be sturdy, it will hold its shape. So I think there's kind of 3 things you could say there, but you're only asked for 1. So if I flick to the mark scheme for that question, so you can pick out any of these properties. So no reaction with water is relevant, the fact that it's unreactive, the fact that it's got a high melting point and low flexibility. So picking any of those properties will get you the first mark, but then you need to explain why. So no reaction with water, why is that important? Because drinks contain water and you don't want them to react with the mug. High melting point, why is that important? Because you don't want the ceramic to melt and you're obviously going to be putting hot stuff in there. Low flexibility, why is that important? Because you don't want the cup to bend out of shape. If you don't give any property, you don't get any marks. If more than one property given, ignore any incorrect properties and associated reasons. So they weren't penalising you if you're saying something that wasn't relevant. The last question here, again, they're giving you all this information. It says a ceramic rather than metal is a more suitable material for wash basins, and why? So if you think of a wash basin, what do you want a wash basin to do? Well, a wash basin has to contain water. You don't want it to react with water. So with a metal, you get a slow reaction with water. With ceramics, you get no reaction with the water that you'll be putting in. So it's only for 1 mark. Give a reason using a property. So you'd say ceramic does not react with water. Yeah, there you go. Ceramic has no reaction with water. So if you look at the booklet, you'll see that there's, quite a bit of information on ceramics and all the rest of it. You don't need to learn all this information by heart. You just need to be able to use what they've given you to answer the few kind of questions that we looked at. And that is essentially it for SC26. So this page here on nanoparticles, you do have to learn. The rest of it you just need to be able to use. It's a short topic. There's nothing difficult in it, but it's definitely coming up. So make sure that you learn it properly.